Hello, everyone. Welcome to Computing Derivatives and Automatic Differentiation with Tovieye Moses Ozi. A little bit about our speaker. Our presenter, Tovieye, has been a full stack software developer for 5 years and is based out of Lagos, Nigeria. He started learning Clojure just 2 years ago and is currently doing back-end development in Clojure at HudStats, which is a sports data acquisition and aggregation company. He says he discovered Lisp via Paul Graham's essay, Beating the Averages, as many of us have enjoyed that essay. And then he discovered Clojure via Rich Hickey's videos, particularly Simple Made Easy. And with regard to Sicmutils, he read an essay by Sam Ritchie on literate programming and became quite interested in the idea of interacting with math and physics concepts from within Clojure. So that led him to the Sicmutils stream, and that's where you can contact him. That's where you can find him on Zulip in the Sicmutils stream there. So please welcome our presenter, Tovieye Moses Ozi, and please take it away, Tovieye.
Thank you, Mark, for that very fine and warm introduction. So as Mark mentioned, I'm based in Lagos, Nigeria. And over here in Lagos, it's actually quite rare to find Clojure developers. In fact, I know of only 2 other Clojure developers personally. There may be more, but it's only 2 I know. So I'm glad that I have the internet so that I can meet up with more Clojure people online. I'm very happy for that. So today, we'll be talking about automatic differentiation. I will share my screen now. Can everyone see my screen? Very good. So we'll be talking about automatic differentiation in Clojure. On my screen, you can see my text editor. I'm using VS Code with Calva on the left, and on the right, a browser window. So I'm using a library called Clerk in order to show my editor window in my browser. It renders the text in my editor into the browser. So with that out of the way, let's get into it. So have you ever seen a math equation? Maybe you are watching a physics video or a math lecture, and you thought to yourself, wow, I would like to interact with this equation, maybe play around with it. And then you think the next thought is, but that would require Python or maybe MATLAB. What this talk will show is that it's possible to do a lot right from within Clojure. And we'll focus on some libraries that help us to do this. And we'll focus in particular on automatic differentiation using the Sicmutils library. I will show you what a derivative is and how you can transform math equations into Clojure functions. I'll also show you how to show some background on how automatic differentiation is achieved in the Sicmutils library. So in order to do all of this, like I said earlier, I'll be using the Clerk library. That is what transforms my Clojure editor text into this nice browser window that you're seeing over here. And I'll also be using the Hanami charting library to plot charts. There will be another Clojure talk that will go into more detail about how to use Hanami. And I think that will be happening on the 21st of November. You can check the workshop site for more details about that talk. Then the library that will be doing the heavy lifting is Sicmutils. Sicmutils is an implementation of the Sicmutils scheme code from a book called SICM. SICM is Structure and Interpretation of Classical Mechanics. This book was written by Gerald Sussman and Jack Wisdom. Many people in Clojure are familiar with SICP, that is Structure and Interpretation of Computer Programs. That book was also written by Gerald Sussman. So the code for SICM was written originally in Scheme Lisp, and some fine Clojurists were able to take that code and port many aspects of it to the Sicmutils library. So that library is what will be doing the heavy lifting for our exploration of maths and physics equations in Clojure. There are also other references that I used in the process of researching this talk. For example, there's a nice article by Sam Ritchie on dual numbers and automatic differentiation. You can find the article in the link in the, and I put it in this namespace for the repo. You can find the link to that article. Let me just go to the browser page here. So here's the article by Sam Ritchie. By the way, I've also posted the link to this repo in the chat. So if you look in the chat for this Zoom call, you'll find a link to the repo, and you can go play around with it during the call, during the workshop, or even after the workshop. So this article was a very fine reference about dual numbers and automatic differentiation. There are also a number of videos about the Sicmutils library, links to them in my presentation as well. So let's look at a sample problem that will help us illustrate how to write math equations or physics equations in Clojure. So let's say you throw a ball straight up and you want to know how high the ball will go. This is called projectile motion. Projectile motion is when a body starts out with some initial velocity and it falls freely under gravity. So the equation for projectile motion for a body going straight up, that is, you can just do a quick search on the internet and you'll come up with this nice equation here. Y equals V naught times T minus G T squared over 2. V naught is the initial velocity, the initial speed with which you threw the ball up. T is time as time passes by. G is acceleration due to gravity. And yes, those are all the terms. And then Y on the other side is the height of the ball. You can see in my Clojure namespace here, I wrote it out. So you have Clojure, these are Clojure comments, the double colon. And if you put, if you can write markdown in your Clojure comments, and Clerk, which is rendering this page, will interpret that markdown. So that's how you are seeing all of this text. And within markdown, you can write LaTeX. So this is a LaTeX expression. LaTeX is a way of writing and formatting math and physics equations. So what you see here is what is rendered as this nice equation over here. So now that we have the equation, we want to put it into our code. We want Clojure to be able to understand it. So equations, we can write out equations as functions. Equations translate very easily to functions. So we can use the Sicmutils library to do this. So on this equation is outputting the height. So this is a function, we'll call it height. And the function takes 3 parameters: the time, the initial velocity, and acceleration due to gravity. And this is a straightforward translation of the function of the equation to the function. And you'll notice that instead of using minus here or star or divide, I'm using versions from another namespace, the env namespace, which is the Sicmutils namespace, which I've pulled into this namespace as env. Now, why am I doing this instead of using the Clojure core functions? If I were now, you see, I evaluate this and it evaluates fine as a Clojure function. What the Sicmutils library does is, for many of the core Clojure functions like minus, plus, divide, the Sicmutils resizes those functions. That is, it extends those functions to work on more than just numbers. So the Clojure core functions work on things like floats, integers, basically just numbers, and just a limited set of data structures. But the Sicmutils versions of those functions is able to work on things like Clojure symbols. To illustrate this, we can rewrite the height function using just the core Clojure functions, which I've done down here. And if I call so this is the version using the core Clojure functions. I call it height core. And this is the version using, so let's call our original version with some parameters. So we'll call it with a time of 0.2, initial velocity of 20, and gravity of 10. Let's see what that evaluates to. You can see the results of evaluation in my REPL down here, 3.8. This is the one version using Clojure core, and we get the same answer. It works fine when you pass in just numbers. But what if you try to pass in symbols? Let me uncomment this line here and call the core version with symbols, and we get an error. But if I call the original version with symbols, we won't get an error. It's able to evaluate symbols, and we'll see that in the next section. So we've been able to translate the equation into a function, and if I evaluate the height function right here, it's a function. But what do you want to render it? You want to see what the function looks like. You can pass in symbols to functions, and you can get back a symbolic representation of your function. So this is the height function. I pass in symbols to it, and this is what I get in my REPL window. Well, this does not really, this is exactly the equation that we started out with, which is this one up here. But we might need to simplify it in order to make it look nice, because all the terms are spread out. In order to do that, I have created a bunch of functions. These functions come from the Sicmutils library, Simplify and infix. Remember, in Clojure, we use we write expressions with the operator in the initial position. I think that is called the prefix notation. So the usual math notation is you have the operator in between your terms. So there's a nice Sicmutils function called to infix, and then it is as a Sicmutils function to simplify your terms. I put all of this together into a function called render. And then we might also want to, there's another function I put together called render Clerk, which takes advantage of Clerk that is producing this browser output and to render LaTeX expressions in a very nice way. And there's a third function which we're going to be using a lot, sRender Clerk. Basically, I simplify before calling render Clerk. So let's try out these functions and see how we can convert functions in Clojure form into nice math notation, into nice symbolic representations. So this function here, this is an expression, and we can evaluate it. Let's try it out. And this is what we get in our REPL. Exponents of sine a plus 3. And if I call render on it, this is what I get in the REPL, sine square a plus 3. And over here in the browser, it renders nicely. So even from your REPL window, you can get a nice symbolic representation. Note that I passed in a symbol to the plus. And this is what the Sicmutils version of plus enables you to do. You can pass in Clojure symbols, and it's going to use that to give you a nice symbolic representation of your function. Let's see what the second one does. There's another function. This time I'm using render Clerk, and the output in the REPL is a map. And you can see the value of the map is a LaTeX expression, which renders nicely to sine square x plus cos square x. So if you don't use LaTeX, you can still get a plain text value, and it will still look nice. But if you use LaTeX, it looks even better. So let's go back to our height function. I'm going to call our height function with symbols as arguments, and I'm going to def that as height symbol, and then render it. So if I render it, this is what I get, text. We just render that, I get a text, and it still looks nice like this. But if I render to LaTeX and put it on the browser, this is the final result. And so this is what our function, after transcribing from the original, this is the internal representation, a symbolic representation of our function. So to recap, equations can be translated to Clojure functions. Math equations are basically a mapping between a value or a set of input values to a set of output values, and you can easily translate that to a Clojure equation, sorry, a Clojure function. And the function we started out with, which is this one over here, is the function for projectile motion with the following terms: t, which is time, v naught, initial velocity, and g, acceleration due to gravity. So we've learned how to put equations into Clojure using Sicmutils, and how to represent those Clojure functions, how to get a nice symbolic representation for them. So let's move on. By this, I think I'll pause a bit for questions. Are there any questions from people in the audience? You can put your questions in the chat. Maybe Mark will tell me if there are any questions in the chat as I move along.
Certainly, and we're also using the Zulip chat, which will be a longer lasting forum for those questions. So let's prefer that for asking written questions. But is everybody following along? Any questions or observations before we move to the next section?
All right, so let's move on. We've been able to represent our equation inside Clojure. We've been able to pull it into Clojure, so you don't need to go to Python or MATLAB for that. Now, we might have some questions about our object that we've thrown up. And so to make this easier for us to ask those questions, maybe we want to see a graph of the height of the ball against time. Can we do that in Clojure? Yes, that is very possible. Before we set out to do that, let's try to simplify our function. Remember, our function took in 3 parameters. So we will convert it to a form where it has just 1 parameter. I think I might be getting ahead of myself here. So we're going to plot a graph, and we'll convert our function from height, which takes 3 parameters, to height time, which takes just 1 parameter. So we'll set our acceleration due to gravity to 9.81, and we'll put that into our formula, and then we'll pick a fixed random. I just picked 40 for the initial velocity. If you're playing around with this repo on your own, you can swap in another value for initial velocity, but I just decided to go with 40. So the initial velocity is now a constant. With that done, our function is now a function of only 1 argument, time t. So you put in time and you get height. So I'm doing this just to make things a bit simpler. So this is I'm going to call this height time function. And we can call height time with initial time of 0.1, and we get a height of 3.95. So in order to make a plot of height against time, we are going to get a bunch of time values. So I'm using a Clojure function range for that, starting with initial time of 0, final time of 8.4 seconds. I picked this final time because that is about the time when, after plotting the graph earlier, that's about the time when the ball returns to its initial position from when you threw it. And we're going to get, between the initial and final times, we're going to be using intervals of 0.2. So that's our time values. Let's see what it looks like. If I evaluate this in my REPL, I get a nice vector of time values. I'm also using this round to 2 decimal places so that I don't get I don't get float or double values with very high numbers of decimal places. So that's what the round to 2 decimal places is doing. And now that I have time values, I can map my height time function across the time values. So that's what this function is doing, and I get a bunch of height values as well. So with those two, we can basically plot our height against time. But before we jump ahead to plotting our height against time, let me quickly tease an operator from the Sicmutils library, the D operator. With this D operator from the Sicmutils library, I can convert the height time function into another function, which I'll call velocity. Remember, height time gives us, we pass in time to height time, and then we get the height. If I do this to height time, I'm going to get a function, and I'm going to call that function velocity. And I can pass time to that function, and I'll get velocity, which is how fast the ball is moving. Let's not go into detail about how the D operator transforms the height time to velocity. We'll circle back to that later. Similarly, if I repeat what I did to the height, but this time I do it again to velocity, I get acceleration. So now I have two functions, velocity and acceleration. I can map velocity against our time values, and I get a set of velocity values. And I can do the same with acceleration and get a set of acceleration values. And all of this is just to set up my plotting function. So we will soon get to plotting. This is a function called line, which I use to calculate if I supply x and a slope and an intercept, I get the y value. I use this to calculate the line. We'll see where it comes in later. So this is how I get my plot data after calculating the time values, height values, velocity values, and acceleration values. I map all of these over. I map my function, which generates a Clojure hash map across all of these vectors. And in the end, I will get a vector of hash maps. Each item in this vector contains a hash map with time, a time key, and several other keys like height, velocity, and acceleration. So that's what's in this data structure, plot data. And now that we have our data for plotting, let's see how we do plotting inside Clojure. For plotting, we're going to use the Hanami library, which is built on the Vega Lite project. Like I said, there will be a separate workshop later on that will go into more detail about how to use Hanami in Clojure to make very nice plots. But the short of it is I have created this data structure that shows how to take my plot data and make a nice 2D plot. So all of this information here is telling Hanami how to. Much of this, I won't go into details. Let's just take it that this is what you need to do to take this plot data and make a 2D plot. And once that is done, I call Clerk Vega Lite function on it. And let's see what it looks like. So this is our plot. And you can see several elements in the plot. On the left side, you have a scale showing the height of the ball. On the x-axis, we have time. And we have a second y-axis, both a second and a third y-axis. So I have velocity on this end and acceleration on this side as well. So, but the blue line represents the height of the ball. So as time progresses, you see the height of the ball increasing. It increases, and at a certain point, it gets to maximum height, and then the height starts reducing. So you can see the plot also shows the slope of the curve. We'll talk about what the slope means. So as I move my cursor, we get a nice slope of the curve at that point. And you can see the purple line that is showing the value of the slope, which is the velocity of the ball. You can see it starts out very high and then steadily decreases. So it starts out in the positive 40, and then somewhere around here, it becomes 0, and then goes into the negative. And then there's the acceleration, which doesn't change. It just remains flat at close to -10. So we'll go into detail about what all of this means. But for now, just focus on the blue line. which is the plot of height against time. Everyone with me so far? Any questions? So at this point, now that we have a nice looking graph, we might have questions about the height and time. So how fast is the ball moving up or down at any given point in time? That's a question you might ask. And put another way, that question might be restated as how much is the height of the ball changing at any given point in time? So how can we calculate how rapidly the height of this ball is changing? We can quickly whip up do some rough calculations for any given point in time. Let's say we picked the point in time 2. We could pass, starting with our initial height function that takes 3 parameters, we could pick a time of 2, pass in time of 2, pass in the initial velocity of 40 and acceleration due to gravity, and calculate the height at that time. So let's check what that gives us. That is about 60.3. And then we could increase the time by a small amount. So instead of a time of 2, we'll change it to time of 2.1. And let's calculate the height at that time. So the height is now 62. So the height has changed from 60 to 62 within 0.1 second. So how fast is the height changing? We take the second height, subtract the first height from it, and divide by the time interval that we use to calculate these heights. And what do we get? 19.8. So this is how fast the height is changing. We're not using any, I've purposely left out units. So, but in the physics world, this would be like 19.8 meters per second. So this is what is called the slope. Basically, you take the value, if you want to calculate the slope of a function, you take its value at some initial point, then you take the value at some other points. If you want an accurate slope for a function that is changing, you might want to keep the interval very small, and then you subtract the first value from the second value from the first, depending on how you arrange things, and you divide by the interval of the inputs. So that is what this little line is representing here. The function for plotting has built in that calculation for slope, and so at any given point here, it is showing the slope at that point. So instead of doing this manually, I've come up with a function that you can just, I call it slope at. It's like generalizes what we did up here over any function. So you pass in a function, you pass in the delta of the input, and you get and then you pass in, the third argument is the value of the input that you want the slope for. And then you get the slope at that point. So if we wanted the slope at a time of 0.05, this is what it would look like. So we don't have to do all of this long calculation. Down here, we can just use the slope at function. And if we want the slope at this is using our original height function that takes 3 parameters. With our height time function, we can just pass in the height time function, the interval. We are making the interval very small, and the value of time at which we want the slope. And let's check what that gives us. So yeah, it turns out to be the same. So the slope at function works. We still get 20.37. So with a slope at function, you can easily tell how quickly the height is changing. Basically, that is what the slope is, how quickly the value of the function is changing. But this is at a specific point in time. And the slope function is kind of an approximation because you have to consider a separate value. You have to put in a small interval, so you don't get the accurate rate of change at that point. So that is slope for you. But what if we wanted to, also one extra point I need to mention is there is a slope for every time. So at the time of 0.5, there is slope, and at the time of 2, there is slope. Just as there's a height for every time, there is a slope for every time. So that means the rate at which the height is changing, or the velocity, is also a function of time. So is it possible to convert, instead of calculating slope for each point in time, is it possible to just take the height function and somehow transform the height function and get a function for velocity? So you start out with a function telling you how the height changes, and you apply some operation to that function, and it gives you another function that tells you how fast the height itself is changing. So the process of transforming that height function to a velocity function, that process is called differentiation. And the velocity function that you get when you complete that process, that velocity function is called a derivative. So that is just the short explanation of what differentiation and derivatives are. So if you call, remember we called our slope at function on for a time value of 2. Let's see the D operator from the Sicmutils library. Let's call it on the height time function. It will give us, let's see what we get. We get a function, it's a Clojure function. And then if we call that function on the value of 2, wow, we get 20.38. And like I told you earlier, the slope function is an approximation. This value we get from using the D function is not an approximation. This is the exact rate of change of the height at the time of 2. And if you want to know what this is, the kind function from the Sicmutils tells you what type of data structure you're looking at. So when you call the D on any function, you get back a function. So the D operator transforms functions to functions, and it is the differentiation operator. So to recap, differentiation is, a derivative is when you have one function and you change that function to another function, and this new function you have tells you how rapidly the original function is changing. So the rate of change of the output compared to the inputs, the sensitivity of a function with respect to change in its arguments, how much the output of a function wobbles if we perturb the function inputs. These are all different ways of restating what a derivative is. And the process of transforming a function into its derivative is differentiation. So that's basically what we did up here. I just called the D operator on height time, and I got velocity, how much the height was changing, and I called the D operator on velocity, and I got acceleration, which is how much the velocity itself was changing. And that's why you see over here, the height increases and then reduces. But how rapidly the height is changing, you can see it's the velocity of the ball starts out high. You throw it up with initial velocity, and then it just keeps dropping. At some point, it becomes 0, and then the value changes to negative. That means it's no longer going up, but it's going down. And I was able to get this by transforming the height function using the d operator to velocity. And then you can look down here and see if we apply the d operator to velocity, we get a straight line. That means the acceleration does not change, it just remains constant. And this is acceleration due to gravity. And all of this is in a nice plot. So we're able to, what I've been able to show here is you're able to do all of this right from within Clojure, this very nice plot. So are there any questions at this point in time? We'll be going on to some heavy material shortly. So let's move on. In calculus, I don't know how many of us did calculus in university or college, but there's some basic calculus that we can easily represent using the Sicmutils library. For instance, if in calculus there's a formula for transforming any equation of the type x raised to x to the exponent of n, so something like x squared. If you want to differentiate that, remember x squared is a function and differentiation is transforming it to another function. So x squared is basically telling us that x, it transforms the value of x by squaring it. And if you want to know how much the output of this function is changing, which is differentiation, to do that, we simply grab the exponent, which is 2, put it on the other side of x, and then subtract 1 from the exponent. So that is how you do differentiation. That's how it's taught in college, the basic rules of differentiation. That's a very simple rule. There are many more rules. In fact, there are a whole bunch of them. Let's try another example. X to the power of 3. So if we want to differentiate that, we'll take 3, put it on the other side of x, subtract 2 from 3, and we get 3x squared. Now, what if you want to teach a program how to do this? Let's see. We'll get to that later, but let's continue working on some basic examples of differentiation. This is a more complex example, x cubed plus 2x squared plus 1. So we can, if we differentiate that, that would be 3x squared plus the 2 will go to the other side, which is 4x, and then we subtract 1 from the power from the exponent, and we have 3x squared. And then the rule is that if you have constant terms, the derivative of constant terms is 0, so the 1 will go away. So all of this that I just showed you, I'm using this function to do it. I just call the d operator on the function. So all of this that is being rendered in my browser is basically the d operator operating on the function. So I call the d operator on the square function, which is what renders as x squared. And I called it on the cube function. Both the square function and the cube function are from Sicmutils. And So the D operator is able to differentiate x squared and give us 2x, and differentiate x cubed and give us 3x squared. And it was also able to differentiate our height time function and give us velocity. So this is, I've defined velocity somewhere up here. This is just like a reminder of what I did above. The velocity is d on the height time function. And so velocity is a function, and we can call it on any time. So a velocity at time 5 is -9. And the kind of velocity is, it's a function. And remember, we can turn functions into, we can see the symbolic representations of functions by passing in a Clojure symbol. So when you quote some Clojure var like this, you're passing in a symbol, and you can render it to see what the velocity function looks like. So here is the velocity function, and it actually turns out to be -9.81 x plus 40. So before we go into how the D operator does its work, let's just talk about some basic application of differentiation. One of the applications of differentiation is to find out the maximum of a function. At the maximum of a function, that is the maximum and minimum of a function, that is where the function curves. At those points, the rate of change of a function is 0, and that means the derivative of the function is 0 at those points. And so velocity at those points turns out to be 0 if you can state it kind of like this. At the maximum of the height function, 9.81 times t minus 9.81 times t plus 40 is equal to 0. And when you solve that equation, you get a time of 4.077. So at that time, that's the maximum height of the ball. So this is how you can easily know the maximum height of throwing the ball. You just take the derivative of the height function, then equate it to set the value of that derivative to 0, and then solve for time. And so derivatives are used to calculate maxima and minima of functions. So let's take a look at the graph again, and you can see it right here. At roughly around 4, that is where we have maximum height, and the slope at the point is 0. That's why the straight line, which is representing the slope, is flat. And this purple line, which is our velocity, if you look at the chart on this side, it's actually 0. So we've been able to see that the D operator is actually a better way of getting the rate of change of a function. Instead of going to calculate the slope and getting some approximate value, we can just call D on your function, and you get another function, and then you can pass in your input arguments and get how much the height is changing at that point, or the velocity at that point. And you can do it again, differentiate your velocity and get acceleration. So now that we've summed all of that up, let's talk about how this is implemented. How is it possible to start with an equation like this, how would you go about coding something like this to transform x cubed plus 2x squared plus 1? Remember, in your calculus rules, there are a whole bunch of rules for how to differentiate expressions. Are you going to write up a separate rule for each expression? That would make it very difficult. So let's just talk about how the differentiation in this library is done, how the D operator goes about its work. The process of doing this in the Sicmutils library is called automatic differentiation. And this approach allows for getting the derivative of not just numbers or functions, but any computer program. And there are other approaches to computational differentiation, other approaches like symbolic differentiation and numerical approximation, but that's not what is happening with the D operator. The D operator is doing automatic differentiation, and it's doing a variant of automatic differentiation called forward mode automatic differentiation. In this version of differentiation, all the numbers that are passed into the D operator are represented as something called a dual. So any term that the D operator sees, it represents it as a dual, and a dual is something like an array or a vector, with two parts. The first part is the original value as we are used to representing it, and the second part is tagged is the derivative of the original value, and we tag that second part with epsilon. So the epsilon you see here is a tag, and it's basically it's like an accounting device. So we will see more as there'll be further explanation down the line. One of the rules that the program follows as it goes about doing this automatic differentiation is any tag values with exponents that is greater than 1 will be thrown away. So, by the way, this nice expression you are seeing here, that corresponds to this one here in my text editor. So I'm basically writing markdown, but in the markdown, I'm embedding LaTeX, and it's being rendered in this nice format over here. So let's play computer for a while. We'll start with a simple expression. So this is a function, I call it test expression. And let's render the function. Remember the rule for rendering, you write out the function, then you pass in a symbol, and you can call render on it, and you'll get a nice symbolic representation of what that function is. So this text expression renders to 2x plus 2 cos x squared. And let's see what happens when we call d on this function. Remember, this test expression is a function that converts x to the output of whatever this is. And then we're going to differentiate this, and let's follow along as the D operator does its work. So step 1, we're going to convert all of these terms, every term in this expression, to their dual form. And all right, before we go into that, I said that in the dual form, the dual form has two numbers, the original value and the derivative of the original value, which we tag with epsilon. And then as we proceed with transformations, if we come across any epsilon with values with exponents greater than 2, we throw it away. There's an explanation for this that makes sense. I don't want to go into a deep explanation for this, but think of it kind of like this. epsilon represents a small, kind of a small value. And think of what happens when you square small values. If you take a small value like 0.01, then you square it, you get 0.001. If you cube that, that is by raised to the power of 3, this is what you get. And with increasingly smaller, higher powers, the values get very tiny and insignificant. So for that reason, if the power of is greater than 1, we basically ignore it. That's not a one-to-one mapping of why we throw away epsilon values greater than 1 with exponents greater than 1. But for now, that explanation will suffice. So let's go back to plain computer. So this is our expression that we started out with, and we're going to convert all of these values to duals. So 2, this is 2 times x. How do we represent this as a dual? So 2 is the original value, and there's a rule for, remember the initial calculus rule for constants. If you differentiate a constant, you get 0. So there is nothing for differentiating a constant. And remember, any epsilon value with powers greater than 1, we throw away. So we can just represent the second part of the dual, the epsilon part of 2 as e to the power of 2. That signals to the d operator that we're going to throw away this part. Then x can be represented as the original x, and then if you differentiate x, that is, x is actually x raised to power 1. So if you differentiate that, you end up with e and 1. Now, how does the d operator know to differentiate x? There are a small set of rules that are built in to the Sicmutils library. So that way you don't have to write differentiation rules for all the functions. You can just build in a small set of rules for a few functions. So for instance, the x to the exponent of n, x exponent n, there's a rule for that. Let's see the code over here. I think it's somewhere down here. So this is the Sicmutils repo, and you can see the exponent function. And over here, you can see the rule built in. So the derivative of the exponent function for any x and y, basically you grab y and you bring it out. So this is the multiplication operator, and then you have x, and then you subtract 1 from y. So that rule is built in. And similarly, there are rules built in for sine and cos. So cos is negate sine, and sine is cos. So you can start with a very small subset of rules. You don't have to code all the rules for differentiation into your program using the automatic differentiation approach. And then, so that's how the program knows how to represent x, to get the dual of x. It just knows that if it sees x, the dual of x is 1. It's able to do that easily. So let's move on to the next term. Plus, here's our plus, 2 times cos x squared. We've already done it for 2, which turned out to be 2 plus epsilon squared. So this is a dual of 2. And multiplied by cos. Now, this is a compound function for which we don't have an inbuilt rule. We only have an inbuilt rule for x squared. So for now, we'll just write our function out. This is the original function, cos, and this is x squared. So we have to get a dual representation of this, and the dual representation of this one is x squared plus epsilon 2x. And what is the dual representation of cos x squared? Well, we don't know at this point. So for now, we'll keep it unknown. This is how the program is walking through the differentiation. So the program does not need to know about your product rule and your quotient rule. Those are all big rules for differentiating compound expressions that we learn in college, but the program does not use that approach. It just starts out with these simple rules. It knows how to differentiate x to the exponent n, knows how to differentiate cos x, and some other basic functions. It knows how to do plus and minus and times and divide. So just working along with all of those, it will come up with a result. So there's also another internal rule that we have to work with. If you have a function and the function is operating on a dual number, so the dual number, this is x. Remember, the dual number has the original value and the derivative of the value. That function is roughly equal to, you can write out the dual form of that function as the function itself, but this time, instead of writing the function with the epsilon value, just the only argument you pass in is the original argument, and then the dual part of the function, the epsilon part of the function, is the derivative of the function with respect to just the original argument without the dual. I don't know if that's clear, but maybe you can take a look at it second time later, and that might make things clearer. So with this rule, let's go to the next step. We started out with this step over here, and let's look at this sub-expression over here. That expression will simplify to this, because this is just basic multiplication. We're going to multiply 2 by this term. So this will be 2x multiplied by 2 into epsilon. And then remember, we're going to throw away anything with epsilon greater than power 1. And so let's not even bother multiplying that. So that is this dot, dot, dot here. So in the end, we end up with 2x plus epsilon 2. And then over here, for this term, we have this dual number over here. And then the program is still trying to represent cos x squared. So taking this inbuilt rule into account, this cos x squared can be represented as this dual, cos x squared plus epsilon 2x minus sine x squared. And then once we have this dual, we can go ahead and do our multiplication like before. And remember, we're not going to keep anything that is multiplied by epsilon squared. So in the end, we end up with this term over here. And just following the rules of multiplication, addition, the basic mathematical operations, and a few inbuilt rules, we end up with this final term over here. And if we look on this side, this is what we started out with. This is the original function. And over here, tagged with epsilon, is our derivative, which is when you add all the terms with epsilon together. And since we're interested in the derivative, the d operator will just throw away the original term and keep the derivative, and you end up with 2 minus 4x sine x squared. So with this approach, you don't need to code in a whole bunch of rules to differentiate equations, just a few basic rules, and then your program knows how to do plus, minus, and some other rules. And with this approach, you can also extend the differentiation to, you can teach your program to differentiate not just numbers, but other data structures. Like maybe, for instance, you have a function that returns a future, a Java future or a Clojure future. You can easily extend, as you can see, you can easily extend the the differentiation operations so that the program knows how to differentiate a Java feature. I know this is getting heavy, but that is how the operator does its work. And in short, the dual numbers, they are like bookkeeping devices that the D operator uses to do differentiation. And there's a lot more happening on that. And even this software statement is like kind of demanding, so we won't go much deeper than this. If you want to learn more, there's a nice paper written by one of the maintainers of the Sicmutils library that goes into dual numbers and automatic differentiation. So you can go and read up more about why just doing subtraction and addition and multiplication, how that is able to create a differential, how it's able to transform a function into its derivative. So that is automatic differentiation with Sicmutils. And before we round up, let's quickly revisit our projectile formula. Before now, we threw the ball straight up, just straight up. What if we increase the difficulty? Instead of throwing it straight up, we're going to throw it at an angle to the horizontal. So here's a function that gives that. I got this function from Wikipedia. So the height of the ball, which is y, is given by the initial velocity multiplied by sine theta naught. Theta naught is the angle with respect to the horizontal multiplied by time minus acceleration due to gravity times t squared divided by 2. So this is a nice graphic of, over here you see in the graphic we have alpha, but that should be theta naught, and initial velocity. So you're throwing the ball at some angle to the horizontal, and the output of the function is the height of the ball. So we can write that out in Clojure as a function. And if we render the function, this is what we get, minus 4.9 t squared plus 4t. I have substituted 40 for the initial velocity, and we're making this a function of two variables. So we can write functions can take in more than one variable. This is what's called a multi-variable function, and it's giving us just one output, which is a height. Now, what if we want to differentiate this function? And remember, this function takes in time as the first parameter and theta naught as the second parameter. This function can, if we just use a D operator, that means we would be differentiating with respect to time and with respect to theta naught. But what if we want to differentiate with respect to time only? So I'm just teasing that the Sicmutils library has even more features than the D operator. The Sicmutils library has what is called the partial operator, which allows you to differentiate a function with respect to only one of its arguments. So if I call partial on the projectile function, I get another function, which is the differential of this function with respect to only time. And I call that function projectile partial. And if I render it in Clojure, this is what it looks like. So 9.81t plus 40 sine theta. And if you remember your college calculus, that is exactly what happens if you try to differentiate this function with respect to time. So you can, although we have a multivariable function, you can differentiate with respect to only one of the arguments. That is also available. A lot of operations are available in the Sicmutils library. Let's do a quick plot of our projectile function. Since our function takes in 2 arguments, we're going to get a range of times, and we're going to get a range of angles of theta naught. So that's what I have over here. And all of this you're seeing in my browser is a rendering of the code in my editor over here, which I've prepared before now. So a range of theta knots, as you can see. Let me evaluate one. So if I do range, I get a range of theta knots, 0, initial value of time 0, final value 8, and intervals of 0.2. So you can see the final value in the vector is 7.8. And for our angle to the horizontal, I'm going with pi over 6. Let's not go into why pi is coming into this equation, but if I evaluate that, I will get this is the output. And so I can plot a surface graph right from within Clojure. So I'm going to map out my projectile function across the time range and the theta range. And this is the data structure that I end up with. You can see it's a vector containing other vectors. So I'm using the for structure in Clojure to do that. Basically, that's a list comprehension. And then I plot it. And if I plot it using Plotly, I think it's something from Python, but it's also available here in Clojure using Clerk. I get a nice 3D plot right within Clojure. So that is, we come to a close of this presentation. From within Clojure, you can interact with functions, write them out, and view their symbolic representation. And you can do differentiation. Differentiation has many applications. For instance, let's say you want to calculate flow rates. How fast, if you maybe you have a tank and you're pumping some water into it, and some water is also leaving the tank, and you have questions about that process, that is handled by things called differential equations, and Sicmutils provide the tools to deal with that. Epidemiology also deals with differential equations. For example, the COVID researchers use something called the SIR models, susceptibility and infected and recovered model. So that uses differential equations as well. Economics, machine learning, optimization and machine learning. So you might have questions in all of these fields, and using the Sicmutils library and the plotting tools and many other tools, you can explore right from within Clojure. This is the docs for the Sicmutils library. You can see it supports many different types of data structures, and you can go and read about it in detail. And like I said, there are a lot of videos on YouTube, about 4 of them that I list in the workshop namespace. So you can go and watch these videos for more details about the SICM library. And with that, I come to the end of this workshop. So the floor is open for questions.
Be shy, everyone. Any questions or thoughts about what you've seen? You want to know anything more about Sicmutils or how auto differentiation works? Well, I guess the presentation was so clear that there was no confusion whatsoever. So we have no questions. Well, that's fine. One more chance. Go ahead.
Oh, yeah. I hope to ask Tovieye, thank you so much for this presentation. Could you tell Tovieye about your hopes, about topics you wish to be using this with, about your explorations with the SICM utils and your hopes for the future?
All right. I hope to be able to use SICM utils to analyze multivariable functions. Like towards the end of the presentation, I looked at a function for the projectile that takes in time and the angle to the horizontal. I was able to plot a surface graph. So that is very nice. There are some other equations out there, like the flow rate equation, and maybe when you watch some YouTube videos, you might see people talking about COVID and the SIR model and the differential equations in there. So there's a module in the SICM utils for solving differential equations. I have not explored that yet, so I hope to build my knowledge in that area so that I can, when I see information like that, I can plug that information into my editor and come up with nice solutions for differential equations and make plots of them. And then also, I'm also interested in plotting stuff in 3D. For example, some mathematical functions have very nice shapes. So I'm thinking of how to plot them in 3D and maybe not just surface plots, but your entire 3D plots of the surface. So that is even beyond SICM utils. We're talking of plotting libraries and other tools in the Clojure ecosystem. But in short, I want to continue exploring the many tools that we have in Clojure for scientific computing and basically working with functions and equations in Clojure.
Excellent, excellent. By the way, we do have a request that came in on Zulip chat that you update your Git repo with any changes that were made to the code that you used during the presentation. So
that is true. I've made a few changes. I will push them out and you'll have the updated version.
Excellent, appreciated.
Can I ask another thing?
Yes, please go ahead.
So could you explain again how you created the plotly plot? I think it was a little bit fast. Was it only needed to just set the points and get the surface? Could we see the code? Thank you.
All right. So the plotly plot takes a Clojure map with data. The data key takes a vector, and you can pass in several surfaces to plot in the vector. So we're only plotting one surface. So we're passing in only one map. And the map, we have the Z key. The Z key is a vector of vectors. So a 2D vector. That's how the surface is represented. And that is why I did a 4 over the time range. So for each time range, I map my projectile function over the x comes from the time range, and the theta range, which is a map itself. So I'm able to create a vector for each value of time range. And so this 2D vector is what I pass to the Z key. Then by default, if you don't pass the X and Y keys, the plotly is going to set your each point on the X and Y axis to 1. So it's, instead of these nice, let's just see what happens if I pull those out. So if I take out and also the type of the plot should be surface. So if I remove X and Y from here, and I evaluate this, and then I plot, let's update our plot and see what happens. So that changed a lot. So the X and Y values don't correspond to the ranges I started out with. I'm a bit hazy on the details, but I don't know why it picked a range of 0 to 10 for, okay, yes, there are 10 values for the X axis. So there are 10 values in our time range, 0 to 8 at intervals of 0.2. So I end up with 10 values. And for our Y range, for our Y range, we have about 40 values. No, actually, I think the time range is the one with 40 values. So if you don't supply an X and Y, each point on the X and Y axis will be set to 1. And so that's why you end up with these strange values which don't map to the actual data. So you need to actually supply your X and Y, which I did, just passing the ranges that you use to generate your X and Y. And then you call the type of the plot surface, and that's how you do it. You get a surface plot. Sorry, was that explanation clear?
Yeah, thank you so much. That helps a lot. Thanks.
So I realize I have one final question, which is when you did the partial derivative, you pass in an argument of 0 to the partial function. What is that parameter 0? What does that do?
Parameter 0 is the index of the argument to the function. So
okay.
This function takes 2 arguments. So 0 indexed, initial index is 0. And so if we wanted to differentiate this function with respect to theta naught, we would pass in partial 1.
Got it. Perfect. So any other questions from the audience? All right, well, we're just about out of time. So I would like to thank our presenter, Tovieye. Really interesting subject and fun presentation, nice graphics. Enjoyed it quite a bit. Like to remind people again that there are 2 more workshops coming up today. They are how to talk with data scientists, which is just a half an hour away. And then I believe it's 3 hours after that, the Devil's Interop for Clojure Interop with Python. So 2 more great workshops coming up. So thank you all for attending and hope to see you at future workshops. And I guess we'll give the last word to Tovieye and Daniel, if you'd like to finish up with any other comments.
I think my final comment is to let the audience know that there is a lot that can be done from within Clojure in the data science and maths and physics computing space. So there are a lot of libraries out there, especially the Sicmutils library, and it's good to play with them and explore, and very interesting. So I encourage you to try them out and also contribute as well, because once more people try them out and make contributions, the feature set will increase and the libraries will be able to do even more.
Excellent.
Thank you so much, Tovieye. It was fantastic.
All right, I think that's it from me. So I'll be leaving now. And if there are any more questions, maybe on the Zulip chat, you can find me on Zulip chat and I can answer more questions or even point you to even more qualified people that can provide better answers to your questions.
Okay. Thanks all.